The questions in the previous video were not clearly visible, so see them again. Okay, pause and take screenshot and solve them. Okay, so let's begin magnetism. The symbol B vector represents a magnetic field. We'll shortly see what it is. Okay. Earth's magnetic field. The Earth also has a magnetic field which is caused by the electric current in the core, but it is similar to that of a bar magnet, which has a south pole like this and a north pole like this. Okay. Sorry. Uh, geologists say that the Earth's magnetic field entirely reverses 10 to power 4 to 10 to power 6 years. It means that uh, in this much time, a time will come when the north pole of the so-called magnet comes like this, and the south goes down. Another things to note are that the north geographic pole is actually the in the direction of the Earth's magnet's south pole, and the Earth's magnet's north pole is in the direction of the geographic south pole. What are the geographic poles? Well, they are the north and south of the Earth's rotation axis. That is, these poles are geographic poles are aligned with the Earth's rotation axis. But the thing to note is that the this so-called bar magnet is actually off axis of the rotation axis, and uh, though it's a very small amount, but it's actually off axis. And the south is here, therefore the field lines go into it. And and also note that the magnetic field lines are always closed loops. This is because there cannot be a magnet with only one pole, though there can be a positive charge. And yeah, only a positive charge, there can be only a positive charge with field lines coming out of it. But in the case of magnets, no monopole exists. That is, the field lines would always be closed. What are field lines? Just like electric field lines were the lines whose tangent pointed in the direction of the electric field, similarly the magnetic field lines are the lines whose tangent point in the direction of the magnetic field. Okay, I hope that much is clear. Now, magnetic needle deflection. When no current flows, the compass points in the north direction, and when the current flows in this direction, the deflection is like this, and when the current is down, the deflection is like this. We will shortly see why this is so. So, continue watching the video. Then we have an experimental law, that is, it was discovered experimentally first and then the theories were expanded or so whatever. So we have magnetic force on moving charged particle. It is equal to the magnitude of the charge times the velocity times the magnetic field times sine phi. Why is that? Well, suppose here is the magnetic field and the positive charge is going in this direction with velocity v, and the angle between the magnetic field and the velocity is phi. Then the component of the velocity perpendicular to the uh, magnetic field is v perpendicular, and it has the value v sine phi. So actually, what velocity contributes to the force is the velocity perpendicular to the magnetic field. Okay, so therefore we get qvb sine phi. As in the first lecture, I had said that V cross B will represent VB sine phi, and its direction would be such that you align your fingers in the direction of V first. Let's do it. Just a minute. Like this, fingers aligned with the V, and then V, it is V cross B, so I move my fingers towards B, and then the thumb, which is out of the page, points in the direction of the force. So actually this force F here is out of the page, V cross B. And the force magnitude is QV cross B, since it's proportional to the value of charge as well. Okay, so this is the direction of magnetic force on moving charge. But the things to note here are that here it was a positive charge. When we have say electrons flowing, negative charges flowing, the Q would be negative, and therefore it would reverse the direction of this force. So actually it would be the V cross B direction reversed. Okay, so V cross B direction was out of the page, so for if this were a negative charge, it would point into the page, the force. Okay, so with this thing we can actually find the force on a conductor moving. Again, shit, sorry.